Okay, so based on this idea that if we have non-spherical error correlations or serial error correlations, then our standard distribution theory for the GLM does not work. The idea for the GLS beta parameter estimator is now to render the GLM such that we still can use the standard theory. Yeah? So let's call this the GLS beta parameter estimator. And the fundamental idea is that if we have a GLM with non-spherical error covariance, which we might write as this, then the distribution theory violated. The idea is that we transform this GLM to a GLM with the transform. So I'm putting a function here now on sigma f. We will not see this, but the idea is that we transform the. It's also not quite correct. No, we actually transform the entire GLM. So we transform this whole thing. So maybe let's call that T as a transform. Or let's call it F, because T sounds like a T statistic. So we apply some form of transform to this, such that the distribution theory is no longer violated. So that's the general idea of generalized least squares. And to make this more specific, let's have a look at the details. So what we assume is that we have our GLM, where as always these are n-dimensional things. This is n times p, this is p, and our epsilon is distributed according to a normal distribution, and now of course with non-spherical error sigma square v. Now we assume that we can transform this, namely by multiplying this whole thing with a matrix A, so that we get on both sides A times A x beta plus A epsilon, where A is actually a square matrix. Yeah. So for that, so A is a square matrix, a multiplication transform, or transform and the transform is times or pre-multiply on both sides with a matrix A. So then we can write this as again a GLM, where we define these entities as follows. Y star is an n-dimensional thing, and Y star is of course defined as A times Y. X star is n times P, and X star is A times X, and epsilon is still n-dimensional and defined as A times epsilon. Yeah. So note that we transformed here the data the design matrix when we do this, and the error, but not the beta parameter. Yeah? So the beta parameter in this transformed GLM is still the original beta parameter. Yeah? So if you assume that this is here the true but unknown beta parameter, we multiply everything by a matrix A, we still have the true but unknown beta parameter in there. And we can, of course, in this new GLM here, evaluate the ordinary least squares estimator for beta, which would be beta hat x star t x star minus 1 x star t y star, which is, of course, just given in terms of our multiples here as this. And is an estimate of original beta true but unknown. Yeah. So far we've just shown that we transform a GLM and then we can estimate by multiplying everything with a matrix, and then we, if we estimate the beta parameter, we still get an estimate for the true but unknown beta parameter, which is good. So the transformation doesn't change the parameter that we're interested in estimating. Now we haven't said anything about this form of the matrix A. And of course, we want to choose the matrix A in some way that the covariance matrix of this is not affected by the fact of the spherical error, of the spherical errors. Of the non-spherical, of the zero correlations in the errors. And to achieve that, what one can do is to define A in such a way that it corresponds essentially to the square root of the matrix V. So to get started on this, assume that V can be written as K times KT for a matrix K, which is actually triangular, but we don't really need to know that much about the matrix K, except that it has the following properties: that the transpose of its inverse is is the inverse of its transpose, and that we also can write V, the inverse of V, as K minus 1 T K minus 1. Yeah? So essentially what we're finding here is a matrix K that you can view as the square root of V, of the matrix V, because if we multiply K with itself, then we get V back. And now we want to actually see what happens if we set our matrix A to the inverse of one of these factors K. Yeah? And what then happens is that our transformed errors, our epsilon star, are actually spherically distributed. So we, in our transformed version of the GLM, in this one here, this transformed GLM, the errors are no longer non-spherically distributed and non-IID, but they are again spherically IID distributed. Why does that hold? Let's have a look. So essentially we need to transform the distribution of the original errors under the multiple K minus 1. And if you remember from the linear transformation theorem, we get that the transformed expectation parameter is the transformation matrix, so k minus 1 times the original parameter, which was 0n, so we have k minus 1, 0n, and the transformed covariance parameter is given by the transformation matrix times the original covariance matrix times the transpose of the transformation matrix. And of course this evaluates to 0n k minus 1, the sigma square we can take in front, and then our v, and this is of course the trick, our v is kt, and then here we have k to the power of minus 1t. We assume that this is the same as kt minus 1. So what we get is 0n sigma square in. Now, so the trick here was to use a transformation matrix A that we apply in or to our non-spherical GLM, to the case where we have a non-spherical error covariance matrix here, and then use the linear transformation theorem for Gaussian distributions to show that the errors of this transformed GLM are again spherically distributed. Now, so in brief, for what in our spherical in our transformed GLM here, if we choose for A the inverse of this square root of v, we have epsilon star being distributed again IID. So we have we have again our standard assumption. Now, if we want to estimate the parameter in this transformed GLM, here this beta, then we of course need to apply our formula, which we've seen above, evaluates to ax t ax minus 1 ax t ay. Now we put in our k to the power of minus 1, which we assume is our A matrix for transformation. So we get this expression. And then with the properties of k, we get to k minus 1, k minus 1 xt, and here we get to xt k minus 1 t k minus 1 y, and this is also the same as k minus 1. And this is also the same as there was a t missing, sorry. There needs to be a t, there needs to be a t, and now these terms are v minus 1. Because that's how we set it up. So we get our generalized squares estimator, which has this form, where you obviously see that the sandwiched multiplication here corrects for V not being equal to In. Because if you have In there, then you get back to our ordinary least squares estimator. And this should be a -1 here, and this is missing there. Yeah. So to write this up again, our beta hat GLS is defined as xt b minus 1 x to the power of -1 xt b minus 1 y. Yeah. So the generalized least squares beta estimator corresponds to a corrected version for the beta ordinary least squares estimator under non-spherical errors. And the correction affects the covariance matrix of this beta estimator. Yeah. Now the question is, of course, where do we get this V from? So how do we get this? And this is actually, if you want, beyond the scope of the course. In linear algebra, one can show that for a positive definite matrix V, which it has to be because it's a covariance matrix parameter, such a matrix K that fulfills these properties always exists and can always be computed based on a single value decomposition, something that we will discuss in the summer term, so we don't have to worry about it. Yeah, so we can always compute it. Now this is the so-called generalized least squares estimator. In fMRI, this is also used, but in with a somewhat different emphasis. And this is the last thing that I want to discuss, namely the notion of data widening. This is a term you find a lot in the fMRI literature. So here the idea is, again, we start from a GLM for which the error parameters are non-spherically distributed. Now again, we apply some transform such that the transformed errors call them epsilon star here are normally distributed with spherical covariance matrix. So that for our transformed GLM, the standard GLM theory holds. And we can use T values in the T distribution to ask about the true but unknown beta parameter. Yeah? Now, the matrix that we use for this transformation is of course the same as previously. So what we use here is a weighting matrix, which we define as K minus 1. We call this the whitening matrix. And if we now set Wy being Wx beta plus WE, E, then our W epsilon is distributed again to a normal with a spherical error covariance matrix. And this is then referred to as the whitened GLM. And here the standard theory holds. Yeah. So this is the whitening approach that we hear in fMRI always about. Now, that is essentially it. So we discussed data whitening and we discussed the generalized least square estimator. One thing that I haven't emphasized, but which was inherent in the whole thing, is that we actually know V. Yeah? So if we want to use this transformation here, we need to know V. So that's important here. Need to know V. Because otherwise we cannot compute its square root, so the K matrix, and we cannot apply this whole idea of data whitening. Now what we have developed so far, if you remember our estimators, we developed estimators for beta hat and for the variance parameter, but we haven't really developed anything that would allow us to estimate this entire thing here. Yeah, so we always assumed it's the identity matrix, so we only have to estimate this one parameter, and we can do it like this. But we haven't addressed the problem at all. If this is not the identity matrix, how can we estimate this matrix? Yeah? And also in what we did today, we assumed that V is known. And if we know V, then we can apply all of this, and we can get to a transformed GLM where we can apply our standard GLM theory. So again here, this holds for known V, because V is KKT. So we either assume that we know V, or we have to estimate it. And of course, in fMRI, we don't assume that we know V, but we estimate it. And this will be the topic for then the next 2 sessions before Christmas, namely questions of covariance matrix, which is the same thing in a way as covariance component estimation. And the way it's done in fMRI is using restricted maximum likelihood. So one can do covariance component estimation in the maximum likelihood setting, but because restricted maximum likelihood is a little bit better, fMRI is done and inherently linked to restricted maximum likelihood estimation. So these 2 topics, covariance component estimation and restricted maximum likelihood estimations, will be then the big 2 topics before the Christmas break. Yeah. So again, today we developed the generalized least squares estimator as the estimator for the beta parameter in a GLM with non-spherical error covariance. It accounts for the fact that the errors are serially correlated by sandwich multiplicating the inverse of the covariance matrix into it. That's the GLS beta estimator, and we can transform the entire GLM to a GLM with spherical errors by multiplying with this whitening matrix and then use the standard theory. This will be a theme and an essential step that will come up like in 2 weeks again, when after we discuss covariance component estimations and restricted maximum likelihood estimation, we will see how this is actually used in fMRI data, where the B matrix is essentially assumed to be known based on pooling its estimates over many voxels. Yeah, so we will get back to this. So today is kind of the first exposure, and we will go back into it. Good. Thank you. That was it.